get going, I had one thing I wanted to ask beforehand. Is there anybody in here who would be interested in being a note taker for this class? One volunteer, back there. Do you mind just come up at the end of class? I'll get your email, and we'll take it from there. Thank you so much. I've started that way. I should have done this in the first place. Sometimes I get too excited to get going. Any questions before we start? You checked everything out? No problems, no questions? Okay. All right. Just let me know if any come up. Okay, so last class period introduced evolution, Hardy Weinberg, and then started working on natural selection right at the end of class. And that's where I want to pick up on now. So this is just an example of evolution by natural selection. We've got these very cute little field mice here, genus Paramiscus. This mouse lives in the woods. You can tell because it's sitting on a bunch of dead leaves, and it is brown. This mouse is a little harder to see, but it's sitting on the sand. It lives in the beach. And it is a tanner color. These are same species of mice, live in different habitats, close to one another, but different habitats. So woods runs into beach. These mice, the coat color differences is caused by one amino acid change. And that was determined by, this is Hopi Hoekstra, who did this work I'm going to tell you about. All right, so her hypothesis was that you get brown mice in the woods and tan mice on the beach. This is kind of a no-brainer of a hypothesis because it allows the mice to blend into their background, right? So hence the example called cryptic coloration. If you are a mouse and you worry about your survival, that's mostly getting eaten. What eats mice? Mice, if you have mice in your house, you know they usually run around at night. What eats mice at night? A lot of it is owls. So owls are, this might not immediately occur to you, at night, owls are visually oriented predators. So they fly around and they look for scurrying mice on the ground. And so the thought is that these mice that blend in have these differences in coat color because they have higher survival because they blend in. And so what I'm going to tell you about is the study she did to evaluate this. So Hopi had her lab all sit around and make mice out of modeling clay. So plasticine mice. They made 250 mice out of modeling clay. If you ever use plasticine, you know that it remains soft, right? It doesn't harden. It's not that type of clay. So after they made the mice, they colored them either tan colored or brown colored, approximating the mice in the natural populations. And then they took these 250 mice, half colored tan, half colored brown, and they took them into the beach habitat and the woods habitat, half of each color. And then they just left them out there. And then they came back a few days later and they looked at these mice and they collected them and they scored each one for beak marks, right? But the idea is the owl comes down, tries to eat the mouse and like, whoa, not right, flies off. So that's the experiment. So these mice were exactly the same except for the color. All right. And in this, this is just a reminder, last time we said there's 3 requirements for evolution by natural selection. Phenotypic variation, we know that exists. There's coat color. We know that this variation is inherited because she showed it's a single amino acid difference. And what she's doing here is looking to see if there's differences in fitness, survival, right? Kind of survival in quotes, right? Because it's beak marks rather than really being how you dead if you're a plasticine mouse. But fitness differences that are associated with its coat color. That's what they're testing for. Okay, so here's the data. It's a little confusing, but these are the mice sitting on the light background. They're on the beach. These are the mice sitting in the dark background, they're in the woods, and this is how many attacks they had. Okay? Clicker question time. I want to know if you think that selection has occurred. And by this I mean whether there are differences in fitness. Oh, I got to turn it on. Base frequencies A. Press and hold power button down for 2 seconds. Hold on here. I got some issues. Yeah, you guys can figure it out while I look for the power button on this thing. I think it has one. No, this one. Yeah. There. Oh, yeah, it's working. Okay, I'm just plugged in. Okay. Yeah, feel free to talk to each other. Okay, just a couple more minutes. Because it looks like most people are in. All right, what I'm seeing is that almost every single person has chosen C. Yes, let's see. Has that selection occurred? Yes, it's occurred in one area. One color reduces attacks. In this area, this color reduces attacks. In the other area, the other color reduces attacks. Yeah, disease is that. Well done, guys. So what's happening then is the mice that blend into the background have higher survival. But one thing to notice here, if we sort of get away from the plasticine mice and we think about mice in general, is that we have 2 habitats, beach and woods. Each of these habitats has a different pattern of selection. Hence, so in this habitat, dark is good, in this habitat, light is good. And this is something to remember when we talk about evolution by natural selection, is that it is very common that it depends on the environment, the population. There's often not one best allele out there, one best type out there. Okay. So with this. I'll stop holding. That's probably helpful. Okay. There we go. So, already said this. So this example fits evolution by natural selection. Moving right along. Okay. So, one of the really important things about natural selection is it creates adaptations. Adaptations are characters that increase the fitness of individuals that have those characters relative to individuals that don't have those characters, right? Adaptations are attributes that increase individual fitness. Now, this is important. Natural selection is the only type of evolution that leads to adaptations. Okay? So, when people talk about evolution, you often hear them talking about selection. And that is because adaptation is what increases fitness. Adaptation is also responsible for much of the biodiversity we see around us, right? So we see a lot of mice that look very different from each other. Lots of forms of mice, lots of forms of flowers, lots of forms of trees. These all represent adaptations to different selective environments. So a lot of the diversity we see around us comes from adaptation due to selection. Hence, if you're going to hear about one form of evolution, it's going to be evolution by natural selection. Okay, I'm going to run through a couple of other examples quickly and then show you how you can adjust Hardy-Weinberg to accommodate selection. This is an example of pesticide resistance. Here, instead of cute little mice, we have, again, rodents, but we have rats, which are deemed to be by people bad rodents. And so this is an example about rat poison. And warfarin rat poison is actually interesting. It is, warfarin is an anticoagulant. It inhibits the enzyme that's necessary for making vitamin K. If you don't have vitamin K, your blood doesn't clot well. Hence, they sell warfarin to people at clearly sublethal doses, but as a blood thinner. All right, so if a rat eats warfarin, its blood doesn't clot well, it gets damaged, and it bleeds to death. This is not important for the example. It's just the interesting biology behind what's going on here. Okay, so in the 1950s, the cities in Europe had, I guess, lots of high rat populations and started putting out warfarin. So this is 1970. So way back here, they started putting out rat poison. About 5 years after they started putting warfarin out, rats were almost completely resistant. They stopped putting it out. And again, in 1970, so this would be 20 years after the initial rat poisoning back here, they put out warfarin. And what you can see is that in a really short period of time, rats became resistant. You could see it if I had mentioned to you that this y-axis is the percentage of rats that are resistant. So in like 6 months, almost all rats were resistant. So really rapid evolution. One reason evolution is so rapid is you can see that these resistance alleles are still hanging out in the population. So the rat poisoning in the 1950s increased the frequency of resistance alleles, and they're still hanging out in the 70s. The reason I wanted to show you this example and what I think it's really good for is they stopped poisoning at this second arrow when all rats are resistant. And what happens, immediately we see the resistance dropping. The resistance is dropping because the way that the resistance work is they're able to develop their blood clotting enzyme, not using vitamin K, but a circuitous route. That circuitous route requires more vitamin K in the diet, so it requires a richer diet that many rats don't get. So when there is no rat poison around, the sort of tried and true vitamin K requiring, where they make their own vitamin K is more efficient, and so you get the reduction of this resistance allele. So we have no rat poison, that's one environment. Rat poison comes, another environment, again, no rat poison. So which allele is favored depends on the environment. It's exactly the same as the beach mouse example, right? Except for the environment is whether the poison is present as a selective factor or absent. Does that make sense? Okay, this is very similar example. You'll see it's again resistance. One of the reasons I have both of these examples in resistance is because people have created very, very strong selection. So it's easy to see a response to it, hence a good example. So this is antibiotic resistance. Again, we have resistance on the y-axis here. And this is penicillin resistance to pneumococcus bacteria in Icelandic children from your textbook. And what you can see is between 1989 and 1994, so this would be a 5-year stretch, resistance, antibiotic resistance goes up a lot. So from about 0 to 20%. Doctors in Iceland realize this. They back off prescribing, and the resistance starts going down. This is a very real thing that happens. This is, I think, a really nice figure. This is seasonal patterns of change in the US. So this is an antibiotic prescription. How many of these prescriptions are written at different times of year, January, February, March, April, May, etc.? What you can see is they write more antibiotic prescriptions in the winter, January, February. That's this line, antibiotic prescriptions. And then this line, I don't know why they made like mustard and orange. They're so similar. This orange line matches the antibiotic resistance. And you can see that it is just lagging the prescriptions. High prescriptions, next month, high resistance. Low prescriptions, next month, lower resistance. So clearly this and the rat poison, very rapid evolution, lots of change in response to this selection. Okay, so what I want to do is, with these examples in mind, now we're in the position where we can say, this kind of thing happens. What I want to be able to do is predict how much evolution you're going to get in response to selection. So say you are in the position where you need to decide, should I cut back on writing prescriptions? Or say you're trying to manage rat populations in a city in Europe, right? Should we put out poison now, or will the rats just become resistant so rapidly it's not worth it? These are the kinds of questions that we're going to try to put ourselves in a position to answer. So we want to predict, if selection happens, how much response will there be? And the way that we can do this is we can go back to Hardy-Weinberg, and we can relax the assumption that there's no selection. So we still assume no migration, no mutation, no drift, and random mating. All four of those we still assume. We're just saying, okay, selection can happen. So now what do? So we're back to where we were last class. Our one locus, the A locus, two alleles, big A and little a. Frequency big A is P, frequency little a is Q, and we're letting selection happen. Okay, and what I want to do is, just to make life easy, we're going to say, let's start at Hardy-Weinberg conditions. Why does this make life easy? Because as we discussed last time, under Hardy-Weinberg, you know how many big A's there are, and that is P squared. 2PQ, heterozygotes, Q squared, little a, little a's. And what I want to do in this example is, I'm going to give you numbers as we go down so you can see how to plug this in. So instead of just using letters, let's also add some real numbers so you can follow that. So let's say if the frequency big A is 0.8, that means there's going to be 8 times 8 is 64, so 64% big A's. Q is going to be 0.2, so 4% little a's, and then 32% heterozygotes. And now let's get to a real population, right? So let's say we have 500 individuals in our population. We can pretend we have 500 rats, okay? We have 500 rats. We know that 64% of them are going to be big A, so there's 320, because this is all our initial conditions, right? 4% are going to be little a, so that's 20, etc. So this is our starting conditions before selection happens. Then we put out our rat poison, and rats die. And you go after, I could have chosen like a less gruesome example, but anyway, you go out after selection and there's dead rats around, and you find living rats and you capture them. And you discover, of your original 500 rats, this is what you've got left. 64 big A's, 32 heterozygotes, 16 little a's. So the rat poison definitely killed a bunch of rats, right? But they didn't all die. Who is left? And the way you figure that out is we want to calculate a survival rate. So we know that there's 64 big A's left out of an original 320. So here's our survival rate. The next one is going to be, so you put this through your calculator. I can't actually do that in my head. and that gives you 20%. So 20% of the big A survive, 20% of the heterozygote survive, and 80% of the little a survive. All right, and this we call absolute fitness. So fitness is survival, and this is just telling us what the survival rate is of these guys. And the reason I say that is because now I want to introduce a concept to you. What I just defined as absolute fitness, that is the survival rate of each genotype. There's a second kind of fitness, and that is relative fitness. And that is how well each genotype survives relative to the other genotypes. In evolution, it's relative fitness that we care about, right? Because we want to know, if we're looking for a change in allele frequency, we want to know if an allele has become more common after selection than it was before selection. So you want to know if your genotype did better than other genotypes. That's relative fitness. Absolute fitness is like if you put out a lot of rat poison and a lot of rats die, or you put out really potent rat poison and a huge percentage die, or very mild rat poison and not very many die. That influences absolute fitness. For relative fitness, you could have very few individuals die, and it still differ among the genotypes. Okay, so this is what we care about. How do we get relative fitness? Actually, a piece of cake. We just take the absolute fitness and we divide it by the genotype that has the highest absolute fitness. So what that does is it gives us a relative fitness of 1 for the genotype that had the highest relative fitness. Fitness is good, right? So that's saying this genotype is the best. And a fitness of 0.25 for these guys. Okay, so a lot of numbers here. Summing it up to what we care about, W, so in evolution, W is always fitness. You may think fitness starts with an F. What's with calling it W? For better or for worse, we name our sort of parameters, or I guess that's what that is, after famous evolutionary biologists. So Sewell Wright is one of the best. So he gets fitness, which is a very important concept. So W is for Sewell Wright. Okay, so we have the fitness of the big A is 0.25, the heterozygote is 0.25, the is 1. All right, so now another question, just to make sure you're following me. So what do you think is going to happen as a consequence of this selection? Okay, it looks like most people are in, so another couple seconds. Okay. What I see is that almost everybody, I must be asking you this. We'll get to some hard ones later. Almost everybody has said B, little a increases in frequency, exactly right. How do we know that? That's because the genotype, little a with the 2 little a's in it, has the highest fitness. Any genotype with a big A in it has lower relative fitness. So we expect the selection to increase the frequency of little a, decrease the frequency of big A. The other thing that we learn by just looking at these relative fitnesses is, big A is dominant, right? Because the homozygote big A and the heterozygote have the same fitness. Selection is acting on them in the same way, suggesting they have the same phenotype. So little a is recessive, and it is favored by selection. Okay. All right. So another concept here, it's a fairly easy concept. S, the selection coefficient. This is a lowercase s. Selection coefficient is 1 minus W. So it's not a new idea, it's a new way of putting it. Selection says, W says how good you are, that's your fitness. S, the selection coefficient, says how bad you are. And it's useful to be able to talk about both. Hence, we have different letters, even though they're completely interconvertible. And S is always going to be somewhere between 0 and 1. So 0 says you're not bad at all, no selection against you, and 1 is lethal. Okay, so we know our relative fitness, we know selection has happened. What we really want to figure out is how much allele frequencies change. So let's start off by looking at our genotype frequencies after selection. Every time you see a prime, it just means after selection. A very logical way, if I was to say to you, how do you think you would figure out what the genotype frequencies are after selection? Or how common is big A after selection? We would probably say, well, it depends on how common big A was before selection. And we know what that is, that's p squared, right? That's how many big A's there were before selection. And how thick big A was. When the rat poison was out there, how well did big A do? This is a pretty decent prediction for how many big A's there are out there, right? How many there were before selection and how good they were at making it through selection. Unfortunately, that's not quite enough. That's what this little weight thing is for. Why isn't it enough? So in order to explain this idea, I'm just going to go to a cartoon of a population. Because I think it's easier to understand. So pretend we have a population of these 10 individuals, 6 circles and 4 squares. And it's very easy. You can figure out if there's 10 individuals, 6 of them are circles. The frequency of circle is 0.6. The square is 0.4. Now we let selection happen and pretend 4 circles are dead. That leaves us 2 circles. So we want to know how common circles are after selection. You look at this and you're like, duh, why are we spending class time on this? It's totally obvious that there's 2 circles left and there's 6 in a population. And so how common circles are after selection is clearly 2 over 6 or 1/3, right? Piece of cake. Yeah. Well, in order to do this, you needed this denominator of 6, right? You needed to know how many individuals were in the population after selection to be able to figure out how common those circles were. And that's called this 6 here, this concept of who's your population after selection happens. That's called mean population fitness. So, all right, got this idea across. In the more complex situation of Hardy-Weinberg, what's the definition of mean population fitness? Mean population fitness says who's left after selection. That's going to be who's there before selection, so p squared big A's, 2pq heterozygotes, and q squared little a's. Each of these multiplied by their fitness, right? That tells you who's in your population after selection. And, I mean, almost don't have to, as long as you have the concept down, you almost don't have to memorize this formula. Okay, whoa. This is our wall of numbers we had created before. What numbers do we need to calculate that mean population fitness? Our p squared, 2pq, q squared, and our fitnesses. So we're going to take these numbers, plug them into this formula, and you have all these on the slide, so you can go back and look at them. So our p squared is 0.64, 2pq 0.32, q squared 0.04, multiply them by their relative fitness, 0.25, 0.25, 0.1, and voila, we get a mean population fitness of 0.28, right? That 0.28 is equivalent to this 6 right here. That tells you who's left after selection happens. So, going back to where we were before, where we say, how common is big A after selection? It's simply who was there before selection, how fit are they, and you divide that by the mean population fitness. And just going to put numbers in. So we have p squared is, again, 0.64, fitness 0.25 divided by mean population fitness 0.57. Here they are for the other two. So let's see how they have changed as a consequence of selection. Before selection it was 0.64. After selection it's 0.57. So the amount of big A has gone down as a consequence of selection. Does that make sense? Yeah, right? Because its relative fitness was less than 1. Same with the heterozygote. 0.32 has gone down to 0.28. Again, makes sense because its relative fitness was less than 1. Whereas little a went from 0.04 to 0.14. So its frequency went up, which is not surprising because its relative fitness was 1. So you can do, as you're doing the math for these sort of things, you can just stop and say, does this make sense? Any questions? All right. So now, that's our genotype frequency after selection. What are our allele frequencies? We would predict the frequency of big A has gone down, right? Because it's been selected against. And the frequency of little a has gone up. Again, you just say, I mean, this is exactly what we did last class. How common is big A? Well, it's how common is big A plus half the frequency of the heterozygote. You plug that in. After selection, 0.57, 1/2 of the heterozygote, and you add them up and you get 0.271. Okay, so how has the frequency of P, or how's the frequency of big A or P changed as a consequence of selection? P after selection is 0.71, before selection it was 0.8, so it's gone down by 0.09. This should match your intuition, right? Because big A and the heterozygote had relative fitness of less than 1, selection was acting against them. Those genotypes became less common while little a became more common. So we would expect P, or the frequency of big A, to be smaller. Okay, any questions? I know this is a lot of numbers fast, and obviously if you're taking a multiple choice test, do you think I'm going to ask you to walk through every single one of these steps on a problem? No. What I'll do is ask you a question that addresses part of a problem, a section of this. But I wanted to walk it through so that you could see how we can use these Hardy-Weinberg formulas and very simply adjust them so that we can predict how much evolution we have in response to selection. All right. So now, what I want to do is take this same topic from a much more conceptual perspective. Okay, so we're going to let the numbers go, more or less, for the moment, and ask whether the rate and pattern of evolution depends on whether an allele is recessive or it's dominant. Okay? The example that we just looked at, the recessive allele was favored by selection. So does evolution happen more rapidly if the recessive allele is favored, for example, than if the dominant allele is favored? All right. So I'm going to acknowledge right now that this is a little tricky to follow, but I have, it's not that the ideas are tricky, the way it's shown on these graphs is tricky, and I've yet to figure out a better way to do this. So I'm just going to walk through it carefully. So we're looking at here, we're focusing on the rate of evolution for alleles that are favored by selection. So if you're favored, we expect the frequency to go up. Allele frequency is a consequence of selection, right? So if you're favored, you're good. So this is a frequency of an allele. It's under selection. Here's time. So we expect the times to go up. Now, we want to start off by looking at what happens if the allele is recessive. And that's these gray lines. Okay, here's a gray line, and here's a gray line. Just ignore the orange lines. We'll talk about that next slide. The initial condition of this allele, this recessive allele, is 0.01. So that's 1 out of every 100. The initial condition of this allele is 0.1. That's the only difference between these two graphs. But in this one, allele frequency increases, and in this one, it stays the same. But the allele is favored in both of them. Anybody have a guess about why these two are behaving differently? All right, let's start this out one step at a time. We're talking something that's recessive, right? So let's just start simply. We're talking about the allele is recessive. That means it's only expressed here, right? It's not expressed here. Well, it's not present there, but it's here, but it's not expressed. Okay, so it's only expressed in the homozygote. If we say, let's look at this. Fancy. Don't ask. Just don't ask. Yeah, okay. So the bottom one, we have a frequency. It's like Harry Potter or something. So the bottom one, we have P is equal to 0.1. All right? P is going to mess you guys up. Think of it as Q, right? The problem is they're talking about AO and A1, and I think it's easier to understand dominant and recessive this way. So where do you have these P, where do you have, screw this, Q. Okay, so where do you have these Qs? We have them here and here, right? So the frequency under Hardy-Weinberg of the heterozygote is going to be 2 times 0.9 times 0.1, right? P and Q. The frequency of this is going to be 0.1 squared. This is 0.01. This is 0.09. This is 0.18. 0.18. All right, so what this is saying is in this lower population, 18% heterozygotes, 1% little. This is favored, and it's 1%. All right, go to this one here. has a frequency of 0.01. 0.01 squared is going to be 1, 2, 3, 4. So 1 out of every 10,000 individuals will be little a in this upper graph. Does that tell you why this one goes up and this one doesn't? Because here, right, if it's recessive, it's only expressed in the little a. If it's rare, 1 out of every 100 alleles, only 1 out of every 10,000 individuals is going to express this favorable trait. In most populations, do you think that individual is even present? Say you have a population of 500. If it's so rare, it only shows up at 1 out of every 10,000 individuals, probably in your population of 500, you're not going to get a little a being expressed, right? So when this is very rare, a rare recessive allele is going to be present in the heterozygous condition. Actually, I could have done that here. So it's going to be 2PQ is 2.09 times 0.01. That's 18. That's, I think that's right. Yeah. So your little a's are going to be present in your heterozygous condition, very rarely expressed in the homozygote. So if a favorable allele is a recessive and it's rare, it's probably not going to get expressed. So the fact that it's favorable is sort of irrelevant, right? Here, where it's more common, it's expressed and it increases in frequency. Initially, it increases slowly because still 1 out of every 100 is not very common, right? So it just takes a while to build up. Does that make sense? Yeah. Why is it 0.09 here? Because here I was jumping, I didn't label what I was doing very well, that's my error. I was jumping to this situation where we had the frequency of little a is 0.01, so therefore the frequency of the heterozygote is 0.01, so PQ. Does that make sense? 0.99. Thank you. So you guys got to keep on me and make sure. I didn't plan out ahead of time. I was going to write this on the board, and that's when I said, thank you. That's why it's not 0.09. That's why you're right and I'm wrong. So what's this? 0.9. 0.0198. Oh, I was close. Okay. All right. Sorry, guys. Oh, man, should not do that in my head. Okay. Yeah. There we go. Now that we have the math right, any other questions? I apologize for that. All right. So, moral of the story is something that's favored by selection, if it's rare, may not increase much in frequency, or may increase slowly. The second thing that I want to say is, what do you know? I had it all right here. So what happens, there it was, 0.99. So, but I don't want to go here. What I want to talk about next is what happens when it's dominant. Okay, so if the allele is dominant, it's going to be expressed, right? And so not surprisingly, whether it's initially rare or initially more common, not hugely common, it increases in frequency when it's favored by selection. But in both of these cases, you see here the recessive line is going up to 1. When an allele is favored and it's recessive, it goes up to 1, and so the big A disappears, the whole population is little a. When it's dominant, that never happens. It's favored by selection, but it never hits 1. Your population is never 100% big A, big A. Why do you think that is? If big A is favored, so little a should be removed by selection. Yeah.
Heterozygotes will still have the little a, but they'll express the big A.
That's exactly right. What he said, taken in here, is that this homozygote and this heterozygote have the same phenotype. There's a little a hiding in the heterozygote, so selection cannot act against it and remove it because it is hidden in the heterozygous condition. So when the dominant allele is favored by selection, it is extremely difficult to fix and to get rid of all of the sort of not as good, the less fit alleles in the population. Does that make sense? Okay, so the so then when it's dominant, increases in frequency, but it doesn't fit. And so I just want to say one last thing about this, and this shows up in your textbook, and also there's a really nice, UVA has a really nice website about this. How many of you are familiar with the eugenics movement? Okay, so a bunch of you, but not everybody. So the goal of the eugenics movement, this was back in kind of the 1930s, mostly 1930s, 1940s. The idea was to improve the quality of the human race by selective breeding. What that really meant was allowing some individuals to not have children. The idea was that we were to improve the quality of the human race. Needless to say, extremely controversial. Even at the time it was controversial, but now, I mean, we just think about things differently now. So, but the eugenics movement, the idea was that we were going to create better people by not letting some people have kids. And so the assumption here was that some people were deemed to be less fit, and they were expressing this phenotype, right? So the goal of the eugenics movement was to get rid of these recessive deleterious alleles. Ignoring all of the sort of ethical issues behind it, and the fact that people who were deemed to be less fit were often deemed to be less fit for reasons that really didn't have a lot to do with genetics at all, but that's a different part of the story. Given what we've just talked about here, do you think the eugenics movement would have reached its goal? No. And the reason is because you can get rid of all these little a's, deleterious recessive alleles, but very few of them. When the favored allele is dominant, most of these deleterious alleles are going to be low frequency, and they're going to be hanging out in the heterozygous condition, and they're not going to get expressed. So by removing these individuals from the gene pool, we don't wind up actually changing the gene pool that much, because most individuals are in the heterozygous condition. And that's here, 0.01 compared to 0.18. Okay, so check out the UVA website if you want. Really interesting. And I will see you guys Monday.
대박? 오, 짜증나.